Okay, so this is a session of exploitation. My name is Hong Hu from Pennsylvania State University. So we have 4 graded papers talking about exploitation for fun and protection. Because we don't have time to introduce you to me for the speakers, please, for the following paper speakers, please come to me maybe in this corner to introduce yourself so I can pronounce your name correctly. So our first work is Untrusted IDE, exploring weaknesses in VS Code extensions. And the author, Elizabeth Lin, are going to tell us how malicious VS Code extensions are going to hack us. So please, Elizabeth.
All right. Hello, everyone. My name is Elizabeth, and today I'll be talking about security vulnerabilities in VS Code extensions. All right. So I'm sure most of you have heard of or used VS Code. It's the most popular IDE out there, and it's built on the Electron framework, which is a JavaScript framework for desktop applications. And one of the reasons it's so popular is because of this extension ecosystem it has. So anyone is able to develop one and publish it onto their marketplace. And it currently has over 50,000 extensions on there. So there are a wide variety of extensions. For example, support for running your programming languages, or you can have linters or themes for your VS Code, or you can integrate databases or containers in there. So if you're using VS Code, you're probably often pushing or pulling to a GitHub repository. And one of the extensions that can help with that is the Git Graph extension. So with this extension, you can easily interact with your repository. It can execute all the Git commands for you. It also gives you a very nice visualization of the remote repository, so you can see all the branches and actions made on it. You can also view file differences or changes between commits, and you're able to do all that within your VS Code, so you don't even have to switch windows for that. So we see how useful these extensions can be, and we're wondering if there are any vulnerabilities in these extensions. And if there are, why should we even care about them? So to answer that, let's take a look at what these extensions are capable of. So they're basically Node.js applications, which means they can import all these NPM modules, which would give it access to your files, your networks, and it can also spin up web servers and execute shell commands and scripts. So you have this application which imports all these third-party code. From a software supply chain perspective, there could be vulnerabilities in these dependencies. There could also be vulnerabilities in the extension itself. And if there are, it would directly affect your user's workstation because it has all these access to your system resources. So to identify vulnerabilities in them, we defined a new threat model, which is different from traditional web apps or Node.js apps, because in traditional web applications, you would assume the user is malicious. But in our case, we would assume the user would not intentionally attack its own workstation. So users are benign, but there would be cases where it could interact with untrusted data, for example, downloaded GitHub repositories. And we also further assume that extension developers are benign. So we're not looking for malicious extensions. We're only looking for vulnerabilities in them. So in our threat model, there's an external attacker who would inject some kind of data, and its goal would be to achieve code execution on the workstation. All right, so let's take a look at the different attack vectors the attacker could use. The first one is related to the VS Code workspace. So imagine an attacker, they could distribute repositories or files with malformed data. If the user downloads it and opens it in the VS Code workspace, it would then flow into the extension. And our second attack vector is network responses. So as mentioned, the extension can make network requests. So an attacker, they could host a malicious web server themselves, or they could do an on-path attack. But either way, they're able to inject through the network traffic some kind of malformed data. And then we have our third attack vector, which are web servers. So extensions, they can open a WebSocket, which can spin up a web server. And if they also happen to open like a malicious website in their web browser, this malicious website could target this open socket and inject data through that. So in all our, in these 3 attack scenarios, we have an attacker that takes advantage of some entry point, and through that entry point, malformed data would flow into the extension. So our approach for identifying vulnerabilities in it is through data flow analysis. We have 4 taint sources mapped to the attack vectors, and we have 3 taint sinks where we identify some type of code execution. So the first one being a shell command, the second being the eval function in JavaScript, which allows you to evaluate string as code, and then the third one being writing to sensitive user files on the workstation. And we built our data flow analysis on top of CodeQL, which is a static analysis tool that supports multiple languages. You could take source code and you build it into a CodeQL database, and then you can construct queries to find specific data flows or code patterns in the databases. So from the 4 sources and 3 sinks, we have a combination of 12 queries we constructed. And an example of query looks like this. So in the top portion here, we have a configuration class where we identify the source and the sink. And in this particular case, we're looking for a source from the web server to a shell command sink. And in the bottom half here, we have something that's very similar to a SQL query. So you have the from clause defining all the nodes or classes you're looking for. And then you have the where clause defining additional patterns you want matched to. And then the select clause, which returns all your results. So we have 12 variations of these queries. But we ran into some challenges running just those basic queries because these data flows don't give us enough information as to whether or not the data flow could actually be exploited by an attacker. So for example, in this code snippet here, we would identify the network response source in line 6, the URL variable, but we're not sure what this value actually is. So to solve these challenges, we added what we call filters. So these are additional data flows or pattern matching that we add on top of our base queries. And in this particular case, it would gather all the values flowing to the variable URL. So it would get the values from line 1 and 2, and you would see that these values are hard-coded, which means it wouldn't be exploitable according to our threat model. So our filters would filter out examples like these. Another challenge we faced was related to file paths, which was a bit more complicated. So in this code here, you'll see we find a file read in line 3, and then it flows to a shell command in line 7. So we need to know, similarly, we need to know what this cache file path actually is. So our chained queries, they would find all the untrusted values flowing to cache file path. And because file paths are a bit more complicated, we would do some more manual review to see whether or not these would be exploitable. So in total, we have 4 types of filters we applied. Some of these are automated filters, and some of these require a bit more manual analysis. More details are in the paper. If you're interested, please go give it a read. So we went through the methods and how we're trying to find vulnerabilities. Let's take a step back and look at our 2 key research questions. The first one related to the software supply chain of this ecosystem. So are there any vulnerabilities in the imported dependencies? And the second question we're trying to answer is, are there any vulnerabilities in the extension itself? And we collected data in the beginning of last year, and at that time there were a total of 43,000 extensions on the marketplace. We found that only 25,000 of these contain actual JavaScript code, which we were able to build into the CodeQL databases for our data flow analysis. All right, so let's move on to some results. So to answer the first question, are there any vulnerabilities in the dependencies? We gathered security advisory data for NPM packages and mapped the highest level advisory to each extension. And we found that more than 9,000 of these extensions actually import a critical level advisory into their application. And another 2,000 import a high level advisory. So this shows that when they're importing third-party code, these extensions are actually also importing risks and vulnerabilities into the application itself. Next one, let's move on to the results from our data flow analysis. So we ran our queries with the filters on top of it, and we found a total of 716 dangerous data flows. Most of these are flowing from the workspace settings source or the file read source. All right. And we have 716 dangerous flows. We wanted to see whether or not they could actually be exploited. So we sampled extensions with higher installations, tried to come up with proof of concepts. We were able to come up with a total of 21 proof of concept exploits, which impact a total of more than 6 million installations. And if you look at the POC column at the right there, you'll see that data flows from workspace settings and file reads to the shell command or eval are more likely to be exploited. All right, so we have numbers for data flows, vulnerabilities, and exploits. Let's go back to the Git graph extension and see what it actually looks like. So our queries, they found a data flowing from a workspace setting in line 3 to a shell command in line 9. So to exploit this, imagine you have in your VS Code workspace this very particular value, which sets the Git path to a shell script. Now you also have the Git graph extension installed. So this shell script value, it would flow through the extension, and it would end up at the spawn sink, which would result in code execution. So an attacker, they could exploit, or they could target Git graph extension users. They could distribute files including this particular value, and then they could launch some type of code execution attack. So VS Code actually has sort of a countermeasure for this. It's called Workspace Trust. Basically, it gives user the option to choose whether or not you want to go into restricted mode. If you go into restricted mode, it prevents almost all code execution, but it comes at a large cost because it disables almost all your extensions and your debugging, and you won't be able to use your workspace settings, etc. So basically, you're left with a pretty basic code editor, which kind of defeats the purpose of using VS Code and installing extensions in the first place. So I use VS Code every day, and I definitely don't want code execution attacks happening on my workstation. So I think the best that I can do without compromising these features of VS Code extensions is to not download untrusted repositories or files and open them in VS Code. All right. So to summarize, we define a new threat model, and based off of that, we build our data flow analysis where we define vulnerabilities, and we were able to come up with exploits for these vulnerabilities that impact more than 6 million installations. We found that data flows from workspace settings or files are most likely to be exploited. And we also found that more than a fourth of these extensions import critical level vulnerabilities into the application. And the queries for our data flow analysis are at this GitHub repository. They have been approved for artifact evaluation. And that pretty much sums up my presentation. I'd be happy to take any questions.
Okay, we are ready for questions.
Hi, Shaochen from UC Riverside. I was wondering, for all those vulnerability you find, is there any remote attack that you can do? For example, the Git graph, I saw it's like a local. You have to the attacker have to change the Git path like locally to like a variable. They can do it remotely, or like any vulnerability you find, you can do it remotely.
Yeah. So if the attacker, for example, they have a malicious GitHub repository, and in your GitHub repository, you would have a file setting this particular workspace setting value. So if you download that unknowingly and then you open it in your VS Code, this workspace setting file would set that particular value. in your VS Code.
Okay, I see. So, but it requires the repo has the VS Code configuration that and they has successfully import this configuration on their local environment, and that will trigger the bug.
As long as you have a workspace setting file open in your workspace, it'll set the value automatically.
Oh, okay.
Yeah.
Okay, so it's better not just open the whole workspace. You can just like clone the code instead, like not having the configuration set up.
Yeah, if you don't want any unknowing file to set workspace settings, then don't have workspace setting files in your workspace.
Okay, thanks.
Thank you for the talk. I'm Choshu from IBM Research. I have 2 questions. Actually, the first one is that I see you are using a taint analysis, analyze data flow between the source and the things. I would like to know how do you identify this kind of sources or things in the JavaScript code, like the fail rate or network-related operations, like these kind of things. How do you automatically identify this kind of operations?
Yeah, so for sinks, we identify places where code execution would happen. And for sources, we identify entry points for untrusted data. So that was based off of our threat model where we have the different attack vectors where untrusted data could come into the workstation.
Okay, and another question is it seems like your work is pretty general for the JavaScript related code, but here, why are you focusing, or why do you emphasizing the JavaScript code related to the VS Code applications?
Yeah. So traditional web applications, you would assume the user is malicious, right? Like the user would try to inject some kind of data into the web app. But in VS Code extensions, we would assume the user is benign. They aren't trying to attack their own system, right? So it's a bit different from traditional web applications. It's specific for the VS Code extension ecosystem.
Okay, thank you.
Okay, I guess we can only afford one more question.
Hi, Roland Yap from NUS. I was just wondering for RQ1, so you actually basically just check a data flow from the source to the sink, right? Are there false positives?
Yeah, in the paper we did mention there were some cases where we weren't able to come up with exploits. It could be
But that could be a different reason though.
It could be for a different reason. So the 21 exploits we found was like a lower bound for this ecosystem. And we only sampled some of these extensions. We didn't go through all 716 data flows because that would take too much time. But there were some cases where we find, okay, we weren't able to exploit this particular data flow.
Okay, so which brings to the next question, which is that, so for the POCs, then were they manually constructed or auto-magically constructed?
Yeah, they were manually constructed. So we went through the data flows and tried to inject.
You didn't look at how to auto-magically construct? Because
No.
it is possible to auto-magically construct.
Yes, it is possible, but we did not look into that.
Okay, maybe future work.
Yeah.
Okay, let's thank our speaker again.
Yeah.